In the last class we had spoken about why the projected gradient method works for the convex optimization case. And I asked you a question that two questions rather. One question was that suppose instead of a convex function, if I replace the objective function by a function which is just differentiable, not convex, and try to minimize over a set x which is convex, then will the projected gradient method be a suitable method? That's a very important question, is whether the projected gradient method will be a suitable method. The issue is to observe that in unconstant optimization we were actually not seeking a minimum, we were seeking something called a critical point, but while seeking the critical point at every step we were trying to decrease the value of the function. So, when we get a critical point, because every local minima is a critical point, we were trying to convince ourselves that under certain good conditions this point x that we get would be quite near a local minima, or okay, we are just happy to get a critical point which we can then test to be a local minima, or which we can or which we know from numerical experience is usually near the local minimum, because we are always decreasing the value of the function at every step. So, our algorithms are called monotone algorithms. Now, for this problem, if x bar is a local minima, no longer a global minima, because I am not talking about convexity. So, let us take a local minima. Then what is the condition for optimality? The condition for optimality here, again noting the fact is a convex set x, can be given in this form. It is not much difficult to prove it, because of this following fact, that now suppose this is my C and this is my C and this x bar is my local minimum, which would mean that there exists a ball of radius say delta around this x, that is, this is nothing but B delta x bar, such that for any point which lies in the intersection of B delta x bar and C, f x must be bigger than f x bar. So, for any x here, any x that is coming from this region, f of x must be bigger than f x bar. So, that is exactly the minimum idea of a local minimum. Now, here I have said this is true for every x you take in x. So, how can I show that? Now, if you take any x, forget okay, any x here which is not in this intersection between the ball and the set, because this is the intersection, and so local in the sense that the x bar is a global minimum of f over this particular set, but it is local over C. Now, if you take any x here, then you join this with x bar by a line, which you can do because this whole line would be in C, because the set C is convex. And then you see that any point here on this line can be written as where lambda belongs to 0 1. So, when lambda is 0 I get x bar and lambda is 1, I get x. So, when I move a lambda from 1 to 0, I am moving from x to x bar, I am moving along this line from x to x bar. So, now if that is the case, then there will be a threshold value of lambda, for example here, beyond which all the these values x bar these vectors would lie in this domain. That is for all lambda greater than 0, but sufficiently small. This is a standard way of writing what I have just told, that, or you can write that there exists a lambda naught such that for all lambda strictly bigger than 0, but strictly less than lambda naught, such a thing will happen, this will be inside this. So, for all lambda greater than 0, but sufficiently small, you have that, have x bar plus lambda x minus x bar belonging to this. So, once this is done, this means that f of x this is true by definition. So, now what I will again do is to apply the Taylor's theorem or apply the definition of differentiability of the function to get so this is equal to and that simply means that now a very definition of small o lambda, which we have discussed earlier when we were discussing the differentiability of a function from Rn to R, then this means as lambda tends to 0 plus, as lambda tends to, this means that is lambda is greater than 0 and lambda tends to 0. So, this will go to 0 and in the limit. So, because x is arbitrarily chosen, I can repeat this argument for every x, proving what I had asked for here, that this should be greater than or equal to 0 for every x. Now, so the same argument about the projected gradient method can now be repeated for this case, but in that case what we will get at the end is no longer a solution, but a critical point. So, at the end what we will get, the end product of the, what is that called, of the projected gradient method as the sequence converges, it converges not to a solution exactly, but to a point which satisfies the fact, a point which satisfies something exactly this condition. Now, it is also important to understand what would happen. I asked you a question, what would happen if f is not differentiable? Then what sort of optimality condition you write? And when, because when f is not differentiable, taking away convexity would only complicate matters, and which is beyond the scope of this syllabus. So, here we will take a convex function phi, which is convex, to be minimized over x element of x, convex function, convex set. And here we no longer ask phi to be differentiable, but we know that at every point, even if derivative does not occur, the subgradient is there, right. Again I recall, for example, this function f x is equal to mod x. Subgradient at 0 where it is not differentiable, that we have done already. See, the technique of finding a subgradient of a convex function is not so easy, if you not so simple, not so easy in general, but for simple convex functions from R2 or it is not very difficult either. Even for very slightly when functions in R2 to R, it is not such a very difficult thing if the function is simple. For example, if I take the expression f x equal to max x square and x, we will try to draw this function and we will try to see how to compute the subgradient. The idea is very simple. Here if you observe all these points, the function is differentiable except 0, at all these points the function is differentiable. So, here along this line on the negative side I take a sequence x k which is going to 0. Here the derivative is nothing but minus 1. So, it is minus 1 minus 1 minus 1, that is at every point of the sequence the grad f x k is minus 1. Here it is plus 1 on this sequence. So, I have minus 1 plus 1 minus 1 plus 1 minus 1 and plus 1, these two values of grad f x k. If you take the limit of grad f x k, it will be minus 1 and plus 1 for this sequence and minus 1 for this sequence, plus 1 for this sequence. Now, I have to take the convex hull of that. If I take the convex hull of that, I will get exactly this one. So, okay, let me leave this as a homework for you. So, what you do, the idea is the following, that if you have a point, so on the real line say x equal to 0 is a solution or x equal to a is a solution, does not matter. So, x equal to a is your solution of the minimum of the convex problem, or whatever, or x equal to a is the point where you want to find the subgradient. Then look at all the points, sequence, construct a sequence x k which is converging to a from the left and all the points which is converging to a from the right. Compute the gradients here and take the limit as x tends to a. Compute the gradients here, take the limit as x tends to a, and then whatever you get there, whatever you get finally, just take the convex hull of that and then basically you get an interval which is our subgradient. So, let just try to draw this and try to do it as a homework. Now, if x bar is a global minimum of this, the global minimum of this problem, how do I write down a necessary and sufficient optimality condition? Now, you understand subgradients would come because there is no other choice, because I have not mentioned explicitly that the function is differentiable. In this case, we have to use the subgradient, but how do we go ahead and use the subgradient? Will such an approach like this work? Because I do not know that there is anything like a Taylor's theorem for subgradients. So, let us start thinking about it. Okay. Now, here you see I am no longer having an unconstrained case, I am having the case where x is also there. Okay. There are many ways to view it, many ways to find the solution, but let us look at certain tools that are required to get this one. Now, Let us just take a definition of the take a subgradient of a convex function phi. So, if xi is in say del of f phi of x bar, then let us see what happens if I take x bar and a point x from x and construct a point which still lies in x by the virtue that x is a convex set, and then try to write down the definition of the subgradient. What I can do is, of course, you will see here the lambda would come extra, lambda of x minus x bar, which I can divide by lambda. Okay. Now, once you have this, what can you do? Shall you push the lambda to the limit? Okay, if I take limit now the question is, does a limit actually exist? Does such a limit exist? The answer surprisingly turns out to be yes, such a limit exists, and it exists finitely, and this limit is usually called the directional derivative of the function phi at the point x bar in the direction x minus x bar. So, this whole expression is now written as a directional derivative of phi at the point x bar in the direction x minus x bar, and that okay. Now, because x bar is a global minimum, one thing is for sure is that phi dash, since x bar is a global minimum, okay, but this is of course true for all x. But what does it tell me about this part? It tells me nothing apparently, but there is a very deep result in convex analysis. I just do not want to prove it, and because I think more discussion is found in the convex optimization course, but a fact that we are not going to discuss too much about it. So, we are just stating these facts that, so one can show for each x there exists xi x such that now what does this show? This shows that if x bar is a global minima, x bar is a global minimum, we can show that for each x there exists xi of x element of del phi of x bar. So, this xi is belonging to del phi of x bar. Such that because of this inequality xi x minus x bar is greater than equal to 0. Okay, this looks to be a reasonable condition for optimality. That is, we are telling that there exists for each x there exists one xi, for each x there exists one xi x belonging to this such that this will hold. If we change the x, this xi x is changing. My question to you is the following, which we will talk about tomorrow in the next, that is in the next class, is that can this condition be strengthened? That is, can the conditions, if I write this as condition A, can the condition A be strengthened? So, if we can do this, this will be enough convex non-differentiable convexity for us, then we will go on to the more standard things. See, our aim is now to tell you about some algorithms about the unconstant case. Can the condition be improved? Means, can I have only one xi which will work for all x? That is what I am asking. Can there be only one xi which will work for all x? That is our question, which we will try to answer tomorrow. Can I have only one xi which will work for each and every x? But today we will go and work on something called penalty function methods, which are very useful methods to solve constant optimization problems, and that is exactly what we are going to do next. Now, let us now talk about the penalty method. So, what does it mean, or what does it mean by a penalty? So, we will first do it in a very general form and then go to some specific cases. So, let me ask you to minimize the function f x subject, or just write subject to x belonging to capital X intersection x naught. So, here I separate the I write the feasible set as the intersection of two sets. This could be for example described by just equality constant, and this could be a constant that x belongs to capital X naught. What it means is the following, that certain constraints which we want to call soft constraints and this is called hard constraints. The reason is this, the idea is that we always want to convert a problem which is a constant problem into an unconstant problem, because that is easier to solve. Penalty function, what we do is we pick some constants from the set of constants and add it with the objective in some manner, and we will show what is that manner. Now, every constant cannot be added, because there are certain constants like that x size is between -1 and +1. These are variable bounds, for example, in engineering problems. They have to be strictly adhered to. You cannot slightly even violate them, because that would lead to safety concerns, for example, in design, the issues would come to that. But for these constants, which we will call a soft constant, slight violation is not a very big thing to be bothered about. Once x is lying between in x naught, slight violation of these constants here is not a cause of great concern. So, what we can do is to somehow plug in this to this, and so make the problem much more simpler. That is, we create a function called a penalty function. Okay. The penalty functions, we construct something called a penalty function. Penalty function is something like this. You define a function p x which will be equal to 0 if x belongs to x. Of course, in most of our operations we should have x also in x naught. P x is strictly bigger than 0 if x is not element of x. Now, take a number rho, take up some rho, real number rho, positive, and construct the function. How do I think of symbolizing? Maybe I will choose the symbol which Ruzinski has chosen as so. The essence of x belonging to x, the soft constants, is encoded in this function. That is, if the soft constants are satisfied, then p x is 0, function value remains, objective remains as f x. If it is not, then p x is positive, that is, you add a penalty to the objective for violating the constants. This is very, very fundamental, and now we can talk about minimizing the penalty of function over x element of x naught. Now, if x naught is nothing but R n, you see this becomes a unconstant optimization problem. But the question would remain, how does the solution of such an unconstant or this simpler constant problem relate to the solution of this original problem, and that is what we are going to investigate at this moment. So, this is what is called a penalty problem. What we do is that we can keep on changing this row and keep on successively solving this problem. So, we shall now relate the solution of the penalty problem or a succession of such problems to the solution of this problem. Before I go and do that relationship, let me tell you that this has a theoretical underpinning which is one of the frameworks of modern optimization, is that if you ask me to solve, if you ask me to look at this problem of minimizing a function x over a set C, then what I can do, I can write this problem as an unconstant problem where when I minimize a function f naught x over x element of R n, where f naught x is written as f x plus del C x, where del C x is usually called the indicator function of a set, where del C x is 0 if x is in C and del C x is equal to plus infinity x is not in C, means theoretically I can attach infinite penalty when x is, when the constraint is violated. So, if I attach infinite penalty in minimization, infinite values are not required. So, basically then we equivalent you are solving this problem, minimizing over C, because only when x is element of C, this function value is finite. If x is not in C, this function value is not finite. So, instead of solving this problem, I can now look at this problem, or my function f naught is no longer a function from Rn to R, but is a function from Rn to R union, or I can just write R union plus infinity. That is, I also you can write as R bar as R union plus infinity. That is, I am considering extending the real line by adding the point plus infinity. So, we are now basically talking about extended real valued functions. So, a real valued function over a set C can be viewed as a minimization of a function f over a set C can be viewed as a minimization of a extended valued function over the whole Rn. So, this idea, this framework actually comes from this penalty function scheme. Okay. Now, what we expect? We expect is the following, that as I increase my rho, as I go on increasing my rho, there will be a rho large enough for which the minimization of this problem would give me a solution of that problem. That is, I am expecting for rho large enough, there would be an x which would, the solution would not only be inside this, which has to be inside this, but will also be inside x. So, let us see what could be the first such result. So, if x for rho greater than 0, right, x star be a solution to this problem, to the penalty problem, maybe I can call this problem as a star problem, penalty problem to star, and if x star is also an element of x, then x star solves this problem, the original problem, say P, x star solves P. This is not very difficult to prove, because whenever x star is a solution of the penalty problem, x star is in x naught, and if you additionally say that x star belongs to x, then x star is a feasible point of P, right. So, we already have that x star now you know that x star is a solution to this. So, basically you know that for that rho f of x star, rho p of x star is less than equal to f of x plus rho p of x for any x in x naught. That is what is given to me. Now, take any x, let x be a feasible element of this problem, that is x is in this, right. Then for such a x, p x is 0, and because of this fact p x star is 0. So, for this it will immediately imply that f x star is less than equal to f x, proving what I had wanted, that x star is a solution of the original problem. Now, we will try to show you that if I actually keep on increasing rho, that is, I take a sequence of rho 1, rho 2, rho 2, rho 3, rho 4, then as rho k goes to infinity. So, I start generating the solutions of this penalty problem for each k. So, for rho 1 it is x1, rho 2 it is x2, rho 3 it is x3 and so on. So, I will suppose this sequence has a bound is suppose bounded or at least has a convergence subsequence. So, then the limit, the accumulation point of that subsequence or the limit point of that subsequence is a solution to the original problem, and that makes, so which means that when I actually try to implement it, I solve this problem for very large values of rho, and then essentially for very large values of rho, for a certain large value of rho I stop and say that okay, this could be possibly my desired solution, but that solution may not be feasible, that will be in x naught, but may not be completely in x. So, we will expect a slight violation in x, but that is actually considered in many practical cases. People take that as a solution because people do not mind a very slight violation in x. So, our result is of the following. So, now you see, let us sorry, I will just keep this as. Now, what we are trying to say is that we are solving this problem for rho 1, rho 2, rho k. So, I am just increasing my, so this is increasing rho 1 bigger than rho 2, rho 2. So, this is of this having this. So, I am just increasing the values and I am solving them, and for each of these I am solving the penalty problem. Suppose the penalty function problem has this solution. Of course, they do not have such ordering because these are all vectors. And you go on. Now, suppose the sequence x k, maybe I should write it as 1, 2 because I am constructing a sequence. So, when I have a vector, I will write the sequence index on the top, and when I have a scalar, I will write it at the bottom. So, x k, suppose x k has a convergence subsequence. And let x star be the accumulation point. Now, suppose somebody now has given you the information that x star actually, that the original problem has a solution. Here you are trying to construct a solution, but somebody has given you prior information that the original problem is has a solution. For example, the original problem could be a linear programming problem or quadratic programming problem, and okay, there are certain ways to know that they have a solution. Suppose the original problem has a solution. Suppose it is given that P has a solution. It is only known that P has a solution, nobody knows what is the solution. So, I am now, penalty method is trying to construct that solution at least approximately. Suppose it is known that original problem P has a solution, right. If it is known that that has a solution, let that solution be x hat. Then what you can write because x hat x k is a solution of p k. So, you can write f of x k plus rho k p of x k you do not know whether it is feasible to the original problem. So, this is not 0 is less than equal to f x hat plus rho k p x hat. Now, p x hat is 0 because x hat is a solution to the original problem. So, x hat is in x. So, basically what you now get is the following, you get p x k is less than equal to f x hat minus f x k by rho k. Sorry, it should be x k. Now, when we define penalty function, we will always consider this penalty function p to be a continuous function. That would be a binding on us, that and that will be helpful in algorithms, that we take this p to be a continuous function. So, what we do here is the following. Now, observe that there is a convergent subsequence x k which is going to x star, and this rho k is going to infinity. So, let rho k goes to infinity. Now, for that particular subsequence, this is also true, because this is true for all k in the sequence. So, hence for that particular subsequence you take the limit, just taking the limit for the particular subsequence. We are not re-labeling this. Now, f x k, f is continuous of course, f x k is going, see in our discussions we largely talk about differential functions. So, continuity of function is always taken. So, please do not say okay, if it is a discontinuous function, then things won't be the same as what we are trying to say. So, here f of x k, you see here f of x k would be like this, that f of x k would go to f of x star. So, it will be the top part goes to a finite value, while this part, so the top part is bounded, while this part is 1 by rho k is going to 0. So, basically which means this whole thing is going to 0. So, this is less than 0, but p of x k is greater than equal to 0. So, limit k tends to infinity, p of x k is greater than equal to 0, but so limit p of x k would also be greater than equal to 0, but here we have less than equal to 0. So, finally, we will get this, but by the continuity of p I can push this limit inside to get p of x star is equal to 0. So, by definition p of x star is equal to 0 means x star must be in x. That is the definition. Definition is always if and only if. So, which means x star is in x. Now, it is only left to show that x star is a solution of the original problem. So, let us see how can or this problem be. So, f of x star limit of f of x star can be viewed as limit of k tends to infinity f of x k. Of course, k is only running over the subsequence. So, we are not bothering about relabeling the sequence and the subsequence. You can, without loss of generality, you can take x k to be going to x star, no problem. Those are just extra writings, nothing else. Now, you see I can always write f of x k. So, I can always write f of x k is always less than f of x k plus rho k p x k, because p x k is a non-negative quantity and rho k is a positive quantity. So, if I add a positive quantity to a number, it will increase. So, which means this f of x star is less than equal to limit k tends to infinity f of x k plus rho k f of x k plus rho k p of x k. Now, this little thing here is obviously less than f of x hat, but f of x hat is independent of k. So, which means this thing, this limit is nothing, it is nothing but less than equal to f of x hat. So, which f of x hat, so which means f of x star is less than equal to f of x hat, but f of x star is just also a solution to the original problem. Maybe when a solution means we are expecting a global minimum, of course. So, let f of x hat be a solution to the original problem, right. F of x hat is a solution to the original problem, global minima. So, f of x star must be equal to f of x hat, but f of x hat is a solution to the original problem, which means that okay, x star is a feasible to the thing to the original problem. So, this has to be true, which would imply that f of x star is equal to f of x hat, and hence x star is also the solution. Now, can you tell me if this idea can be extended to local minimum? Can you handle this? So, homework is, can you develop these results for the local minimum, or these are just for the global minimum, which we should not be, we should be able to find a local minimum. Can you develop these results for a local minimum? Thank you very much. So, we will continue our discussion of penalty functions there, and tomorrow in the next class, where we will take x as certain functions, in the sense that x described by certain inequalities and x naught is a fixed set, and then we will try to discuss about it, and then we will discuss a very important concept called exact penalty functions. Thank you very much.